Hello, I'm Yoon from Dongguk University DTM Lab. Today, I'll be presenting a paper review on the topic an explainable AI model for text-based patent novelty analysis. First, here is the bibliographic information of the paper. This study was published in 2023 in the journal Expert Systems with Applications. The aim of this research is to develop an explainable AI model that evaluates technological novelty based on patent claim comparison. The presentation follows the same structure as the paper. Novelty is a mandatory requirement for patent applications and refers to a new embodiment. Because novelty assessment is critical, it has been widely used in the field of technology intelligence. Previous studies on patent novelty have focused on technological originality. These studies typically assess novelty based on patent databases, which are valuable resources that directly reflect technological innovation. Novelty analysis can be approached through bibliometric indicators or textual information. In particular, deep learning-based approaches are effective in capturing the complex features embedded in patent claims. However, research that evaluates novelty and patentability solely based on technical content is rare. It is essential not only to ensure accurate research, but also to provide clear evidence and human understandable explanations. Prior studies have proposed frameworks for assessing novelty using patent databases. Representative approaches include bibliometry indicators, outlier detection, and deep learning-based prediction methods. In particular, there have been active efforts to classify novelty using NLP-based deep learning models. This study proposed a novelty analysis model that incorporates both technical term-based embeddings and patent claim structures. In the NLP field, embedding models are used to run hidden features within text and are applied to text such as classification and inference. However, the black box issue remains a major concern. Therefore, it is important to develop models that can provide human understandable explanations for inferred outputs. XAI models can be categorized into local and global approaches, as well as self-explaining and post-hoc methods. Local approaches clarify the output or rationale for a specific input, while global approaches describe the overall prediction process regardless of specific input. Self-explaining models generate explanations during the prediction process, whereas post-hoc methods generate explanations after the prediction. This study focuses on a self-explainable and local explainable XI model, designed to identify and explaining which claims and technical elements and evaluated as novel. This study proposed a framework that assesses novelty by comparing prior art with a target patent. Figure 1 illustrates the concept of the proposed model. The XAI model includes a function that explains the prediction by identifying key claims highly relevant to the outcome. The proposed framework consists of three modules: dataset, model, and application. First, a training dataset is constructed based on pairs of target and prior patents for novelty analysis. Next, a self-explainable model is proposed to encode textual information while capturing dependencies between patent pairs. Finally, the trained XAI model is applied to demonstrate how the results can support R&D planning. This study constructs or training dataset based on patent document pairs. EPU full-text patent data is used as the training source. Such reports provide the most relevant prior art for a given patent application. In this study, patent pairs are labeled for novelty classification using category X information from the search report. Patent pairs are constructed using cases classified as category X, linking target patents with their prior art. These pairs are then labeled for binary classification into class 0 and class 1 based on novelty. After labeling, the dataset is expanded using patent examination histories. Text input data is structured based on dependency relationships between claims. Claims are categorized into independent and dependent claims. For each patent, a claim set is defined using an independent claim and expanded by including its dependent claims. The model is trained on these claim sets, enable novelty assessment by reflecting the structural relationships among claims. The XAI model is designed as a self-explainable text classification model for evaluating patent novelty. It consists of an input layer, a pairwise claims layer, an interpretation layer, and an output layer. First, in the input layer, claim sets from the target and prior patent are entered. Context-preserving embeddings are generated by reflecting the structural relationships between independent and dependent claims. As a result, each claim set is represented as a d-dimensional vector. Next is the pairwise claim set layer, or combinations between the claim sets of the target and prior patents are generated to extract comparative features between the vectors. Next, in the interpretation layer, weights are run for each generated claim pair. This allows the interpretation of how much each pair contributes to the novelty decision. All pairs are then aggregated into a single output vector through weighted summatation. Finally, the output layer performs binary classification of novelty using softmax. Cross-entropy loss and a lambda term are applied to stabilize training and limit the number of interpretive claims. The model predicts novelty based on the relationship between the target and prior patent, using the most recent 10% of data for testing. In addition to simple classification, it provides explainable results by presenting the contributing claim set and pairwise scores. The training dataset is built using the full EPU dataset. Patent pairs are extracted based on the inclusion of such reports and English language documents. Data is filtered around the category X and refined using noise removal conditions. The final patent pairs are constructed using the augmentation strategy shown in Table 2. This study conducts experiments using the previously constructed novelty evaluation dataset. The model adopts a self-explaining text classification approach. As a result, it outperforms patent match by over 20% in accuracy, while reflecting claim dependencies and enhancing critical applicability. Lambda controls the degree of weight learning based on the importance of each claim set. Larger values makes the model focus more on explainable claims. The results in Table 4 show that tuning lambda is essential to balance interpretability and performance. Novelty inference was conducted in the field of vehicular communication, using the lambda value that showed strong performance in previous experiments. 2 out of 7 cases were actually granted after passing novelty examination. 1 was withdrawn, and the rest are still under review. Please refer to Table 5 for details. The model provides both the novelty prediction and the claim sets that contribute to the decision. This enables an interpretative XAI-based patent evaluation framework. For details, please refer to Table 6 and Table 7. They proposed a method for building a patent novelty evaluation dataset using EPO search approach. While similar to the patent match dataset, it differs in two key aspects. Patent match treats both category X and Y as novelty blockers, whereas this study uses only category X to establish a clear standard. It also presents a binary classification framework applicative to real-world patent examination and R&D planning. The model classifies the novelty of patents and identifies the claim sets that influence the decision. This allows for early detection of potential infringement, supports R&D direction setting, and can be applied to emerging technology analysis. This study proposed an XAI model for evaluating patent novelty. The XAI model addressed the black box issue and enhanced interpretability. The approach can support patent examination and R&D planning. However, a limitation is that the study was conducted across all technology domains without field-specific separation.